Hello everyone, Godongwane the Nated God here. Right, so now in this lesson, I just want to show you how the knowledge of angular motion is actually in tandem with how we go about solving problems based on flywheels. Right, now if you have to pause the video, you can do so to read the statement and write down what information has been given. Right, but I've already taken the liberty of doing that. In the statement, we are given the flywheel has an outer diameter of 900 millimeters, so you essentially have an outside diameter of 0.9 meters, inner diameter of 600 millimeters. That's the inner diameter, so di, right, is denoted as, this is how we denote the inner diameter, is 0.6. We have the width, which is 0.2. Right, now this part of the flywheel essentially is the rim. Right, it is the rim that has an outside diameter as well as an inside diameter, and the length of the rim we essentially take as the width. Right, the machine performs 12 punching operations per minute. Right, so we've been given the the frequency at which the punching operation takes place every minute. Right, so those are 12 punching operations per minute. That's the frequency. Right, and then we're also given the density of the material of the flywheel, as well as during each punching operation the speed of the flywheel drops from 210. So we have N1, which is 210 revs per minute, and N2, which is 132 revs per minute. Right, now they do say neglect the mass of inertia of the spokes and the hub and calculate the following. All right, 3.1. Let's calculate the mass of the flywheel. Right, so this one will be straightforward. Essentially, we are being asked to calculate the mass of the rim because we are ignoring everything else, or we are ignoring every other part of the flywheel. Right, as per the statement, neglect moment of inertia of the spokes and the hub. Right, so the mass, right, the mass of the flywheel, right, will be equal to rho, the density, times the area times the length. Now what does that look like? This will be the rho, the area. Right, you have an outside and inside diameter, so we'll simply use pi into RO squared, so the radius of the outside, or the outside radius squared, minus the inside radius squared. Right, times length, which essentially is the width. Right, so now we substitute this is equal to 7300 kilogram per cubic meters times pi into RO. Right, now the outside diameter is 0.9, meaning the outside radius is 0.5 squared, minus inside radius, inside diameter is 0.6, which means the inside radius is 0.3 squared, times the width is 0.2 meters. Right, so that's 0.2. Right, now if you punch this in your calculators, we get 516.007 kilograms. Right, now let's look at 3.2, the moment of inertia of the flywheel. Right, now moment of inertia, to get the moment of inertia, right, moment of inertia of the flywheel will be equal to the mass, right, of the flywheel times the radius of gyration squared. Right, now this part of the flywheel in particular is circular. Right, and how do we get the radius of gyration squared for the a part in a flywheel that is circular? So this will be mf times, now how do we get k squared, the radius of gyration squared, for a part in a flywheel that is circular? Right, all you do is you take, right, we take how we calculate that part, the radius, not the radius, you take how we calculate the area. Right, yes, the area of that part. Right, and you'll simply replace pi with half, right? So seeing that this is hollow, right, hence the minus when calculating the cross-sectional area, right, we take how we calculate the area, we replace the pi with 0.5 and replace the negative sign with the plus. So essentially here you will have, so replace this with half, so half into, this remains exactly as it is, but this is now plus inside squared, right? That is for any and all parts that are circular, right? How we calculate k squared is you take the area, right, exactly as it is, you substitute pi with half, right, and if it's hollow, you replace the negative with a positive sign, right? If it's a solid one, remember, if it's solid, then how you calculate its cross-sectional area will be not half, will be pi essentially r squared, right? Normally this is how we calculate the area of a shaft, right? So meaning when having to calculate the k squared, so the radius of gyration squared, right, all you would do for this one is you would take how we calculate the area but replace pi with half r squared, right? So that's what I mean, right? Now we substitute. So this is 516,007 times half into the radius is 0.45 squared plus 0.3 squared, right? Now if you punch this in the calculators, we are going to get 75,466 kilogram meter squared, right? This is 3.2, which is 3.2. Right, look at 3.3. 3.3 calculates the kinetic energy absorbed during the acceleration period of the flywheel, right? During the acceleration period of the flywheel, right? Now, essentially the kinetic energy absorbed, they're referring to the energy being supplied by the flywheel, right? So remember that the flywheel is a device that essentially hubs energy, and the way it does that is through kinetic energy, right? It stores energy, and the way it does that is through kinetic energy, right? So hence we simply are going to use this here, the energy being supplied by the flywheel, right? That energy is stored through the change in kinetic energy, so this will be half times the inertia of the flywheel. Remember, this is angular motion, right? So we do not necessarily use half mv squared, but instead of the mass we use the inertia, right, times omega 2 squared minus omega 1 squared, right? Right, now we substitute, so this will be half into I is 75, so this is 75,466, all right, times, now you do remember that to convert the rotational frequency, right, to angular velocity, remember you have this relationship, right? Omega, which is the angular velocity, is equal to 2 pi n, right? And then because this is in, the n is in revs per minute, then you would obviously have to divide by 60, right? So that is exactly what we must do here, right? So this then becomes 2 pi times essentially n2 Now what is N2 equal to? 132, right? So N2 is equal to 132, right, divided by 60. And then of course we square this minus the 2 pi times N1. N1 is 210, right? So this will be 210 divided by the 60, right? All of that squared, right? Now if you punch that in your calculators, we are going to get negative 11,038 kilojoules, right? Which essentially therefore means that the EK absorbed, right, is equal to the 11,038 kilojoules, right? Right. 3.4. Calculate the torque required to accelerate the flywheel between punching operations if the duration of each operation is 1,2 seconds, right? Now they are saying we must calculate the torque required to accelerate the flywheel, right, if each punching operation, if the duration thereof is 1,2 seconds, right, in each operation. So essentially what they've done here is that they've given us what is this, T1. Remember we have a frequency, right, a frequency which is in terms of the punching operations per minute, right? So what we do is, this is 3.4, right? To get what they've essentially done is give us T1, right? So this here is T1, right? Because essentially this is the punching operation, right, or the duration thereof in each operation, right? So we are essentially able to take that as T1, and to get T2 we use the frequency, right? I don't know if you guys remember, frequency is equal to what is this, is equal to 1 over T, right? And then to get T, essentially this will be T2, right? So I used F here, I used N is the frequency, which is 1 over time, right? Now this here is elementary stuff, right? But this is how you essentially calculate frequency, right? Hence whatever you get here will be either per second or per minute, right, depending on how this has been expressed, right? To get T2, right, you essentially then say 1 divided by N, which is the frequency, right? 1 over N is 12, right? Now 12 is per minute, right? So we convert that to seconds, obviously. So if you're to convert this to seconds, that you divide by 60, right? Meaning essentially this is equal to 60 over 12, right? Therefore, meaning T2, now if you punch this in your calculators, right, 60 divided by 12 is 5 seconds, right? So we essentially have T1 as well as T2, right? Remember that in calculating torque, now there's a number of ways we can do this, but one of the ways, which is the one I'm going to show you first, right, is to calculate the acceleration, right? We already have the moment of inertia. Remember, torque is equal to inertia times the angular acceleration, right? So in trying to determine the angular acceleration, we are going to use equations of motion, right? We're going to use equations of motion. So in using equations of motion, you're going to need the change in T, which is equal to T2 minus T1, right? So T2 is 5 seconds minus T1, which was that 1,2 seconds, right? Now if you punch this in your calculators, we get 3,8 seconds, right? And then in calculating the angular acceleration, we know this is equal to omega squared minus, not omega squared, omega 2 minus omega 1 divided by the change in t. Right, now all we do is substitute. Right, now in substituting, this will be essentially, this here will be 2 pi, right, into n2 minus n1, right, divided by essentially 60 times the change in time, right? So this will be 2 pi into n2, which is 132, right? Yes. So this is 132 minus 210, which is n1. Well, this divided by the 60 times change in t, which is the 3.8 seconds. Right, now if you punch this on your calculators, you're going to get negative 2.15 radians per second squared, which therefore means that this here is actually equal to 2.15 radians per second. Right, now we can calculate the torque. Right, accelerating torque, which is what they're looking for, is equal to the moment of inertia times the acceleration, angular acceleration. Right, remember when we calculated, we got the 75,466, right, times this here 2.15 radians per second. Right, now punching this in our calculators, we are going to get 162,252 Newton meters. Right, and that is how you calculate this. Right, alternatively, right, to really show you now that if you have the knowledge of angular motion, right, essentially the sky's the limit as far as flywheels. Right, I'm going to show you an alternative method. Right, alternatively, you could have taken this approach and it would have been acceptable as well. Right, now we do remember that what is this work done? Right, work done in terms of angular motion is equal to the accelerating torque times the the angular displacement. Right, so that means in order to calculate torque, you need to have the work done as well as the angular displacement. Right, angular displacement being in radians. Right, essentially we've already calculated this here is equal to, so essentially the energy being supplied, right, for this case is essentially equal to the energy being supplied by the flywheel, and this is equal to the work done. Right, so essentially, because we've already calculated this here, right, we've already calculated this. Remember, in this case we are only looking at the flywheel, right, only the flywheel. We are ignoring any and all other components. Right, hence the energy being supplied, right, is only from the flywheel. Right, meaning that the work done is essentially being done by the flywheel. So seeing that we've already calculated this, it means we have the work done. So all we need to do really is to calculate this here, right, theta. And how we calculate theta? We calculate theta by using what is this? By using what is these equations? Kinematic equations. Right, one of the kinematic equations is theta is equal to omega squared plus, not omega squared, omega 2 plus omega 1, right, divided by 2, right, times the change in t. Right, this here is the average angular velocity. Right, So this will be equal to essentially 2 pi into n2 plus n1 divided by the 60 times 2 times the change in t, right? So this, substituting, we get, this is 210 plus 132 divided by the 60, right, times the 2 times the change in t, which is that 3,8, right? Now if you punch this in your calculators, we are going to get 68,047, right? Now don't be confused here, right? Essentially I swapped these around because it doesn't really matter, right? So if you said 132 plus 210, you are essentially going to get the same thing, right? So the order of the rotational frequency doesn't matter because we are adding them anyway, right? So this is in radians, right? Once you have that, right, now you can go back to this formula. We've already established that the work done is essentially being done by just the flywheel, so we can use that energy being supplied by the flywheel, which we've already calculated, and then solve for the accelerating torque, right? Flywheels is a matter of looking at what you've been given and use what you've been given to get what you are looking for, right? So this times that, therefore meaning making the accelerating torque the subject of the formula. This will be the work being done divided by theta, right? So this is equal to the energy being supplied by the flywheel is this 11,038. So this is 11,038, right? This is in kilos, so times 10 to the 3 divided by the theta we just calculated, which is 68,047, right? Now we punch that in your calculators and we get 162,211 Newton meters, right? Which essentially is more or less the same as what we got when using the other method, right? So again, flywheels is a matter of looking at what you have and see how you can use angular motion to get it, right? So now we are going to look at 3.5. 3.5 is calculate the motor power required for 12 punching operations per minute, right? This one is pretty straightforward. How we calculate P in. That's the input power is essentially equal to the energy being supplied by the motor times the frequency, right? Now we've already established that this here is equal to the energy being supplied by the flywheel, since we are only looking at the energy being supplied by the flywheel, or since we are only looking at the flywheel, right? So essentially we have this, we calculated and got the 11. So this is the 11,038, right, times 10 to the 3, right, times n. N is 12 per minute, so this will be 12 divided by 60, right? And if you punch this in your calculators, you're going to get 2,208, and I've expressed this in kilowatts, right? Very easy stuff here, right? So hopefully you've learned something here, right? If you have, please click the like button, right? Also share this with your fellow students, right? All the best.